Good evening, traveler. You found science, where the universe behaves like a cozy bedtime story. Tonight we float toward a giant that never stops stirring. A world wrapped in stripes, storms, and swirling colors. A world so big Earth would be barely a crumb inside. Close your eyes if you want. Jupiter doesn't mind being admired half asleep. Before we begin, I'd love to know where in the world you're watching from tonight. There's something comforting in knowing that somewhere out there, thousands of us are looking up at the same sky. If you enjoy these peaceful explorations of science, please give the video a like and subscribe to the channel. And to those already part of this sleepy community, thank you so much for being here. Don't forget to click the little notification bell so you won't miss the next quiet adventure among the stars. I always hope these stories help you relax. But if this one happens to be too interesting and keeps you awake, well, at least you'll fall asleep a little wiser. Now, as the stars begin to blur and the mind settles, follow the soft glow of a distant world, a planet of storms, light, and mystery. What truly makes Jupiter the king of planets? In the beginning, there was dust, fine, cold grains swirling in the newborn sun's faint light. Within a few million years, that dust gathered into worlds. But one of them grew faster, hungrier, and more powerful than the rest. Jupiter. It was the first to form, and by doing so, it reshaped everything that followed. Its immense gravity sculpted the solar system, hurling some worlds inward, flinging others out, and quietly deciding which would survive. Every small planet and wandering comet has in some way felt its pull. Yet this giant, for all its power, has no solid ground. What we call its surface is only a sea of clouds stacked in bands of cream and ochre, striped by winds that race faster than any storm on Earth. Beneath them lies a world of pressure and heat, so great that hydrogen itself turns metallic, forging a hidden ocean of liquid metal that glows faintly in the dark. Jupiter is not only a planet, it's a cosmic archive. Its chemistry preserves the earliest whispers of the solar system's birth. Its storms record the restless energy of a world that never truly sleeps. Its magnetic field stretches so far it could engulf the sun itself, wrapping space in invisible ribbons of light and radiation. And around it orbits a miniature solar system of its own dozens of moons, each a world with a story: volcanic Io, icy Europa, vast Ganymede, and ancient Callisto. Together they dance in rhythms of gravity and time, bound by the pull of their colossal parent. This journey will take us through all of it, from the swirling birth of the planet to the whispering edges of its magnetosphere, where charged particles paint the night with auroras brighter than any seen on Earth. So let's drift closer now, slowly through the dark. The king of planets awaits, turning endlessly beneath the quiet light of the sun. Long before Earth ever formed, when the sun was still a young and temperamental star, a cloud of dust and gas circled it like a soft, spinning fog. Within that haze lay the ingredients for everything to come: ice, rock, and the simplest atoms the universe could make. But something extraordinary happened in one region of that vast disk. Matter began to gather faster, clumping together with such greed that it soon became the largest planet in the solar system. Jupiter was born from gravity's hunger. To understand how such a giant came to be, scientists have proposed two main stories. The first is called core accretion, the idea that Jupiter began as a solid embryo, a rocky, icy core that grew by attracting nearby debris. Picture it like a snowball rolling downhill, but in space. Every pebble, every dust grain it met was pulled in by gravity, and the snowball swelled. Once this core reached a critical size, around 10 times the mass of Earth, it became powerful enough to start capturing the surrounding hydrogen and helium gas before the newborn sun could blow that gas away. What began as a frozen pebble collector turned into a world wrapped in the lightest elements of the cosmos. The second idea, known as disk instability, paints a different picture. Instead of slow, steady growth, it imagines that Jupiter was born in a kind of cosmic landslide. The disk itself became so massive in certain regions that gravity caused it to collapse directly, forming a giant planet in one sweeping moment. This would explain how Jupiter could form so quickly within just a few million years, a blink in cosmic time, before the young sun's radiation stripped the disk of its gas. In truth, reality may be a blend of both ideas. A solid seed forming first, followed by a rapid inflow of gas aided by the unstable, turbulent disk around it. Timing was everything. Jupiter had to form early, while there was still enough gas left in the solar nursery to build its immense atmosphere. Most of the disk's gas was gone within about 10 million years, so Jupiter's growth had to be a race against evaporation. If it had waited too long, it might have ended up as a smaller, Neptune-like world, but it won that race spectacularly, swelling into a planet so large that it holds over twice the mass of all the other planets combined. The composition of Jupiter's atmosphere offers quiet clues to its beginnings. It's made mostly of hydrogen and helium, the same ingredients as the Sun, but with higher levels of heavier elements like carbon, nitrogen, and sulfur. That enrichment tells us Jupiter's building blocks weren't just simple gas. They included icy planetesimals, perhaps comets, and frost-coated rocks, drifting through the cold outer regions of the protoplanetary disk. These icy fragments likely carried volatile molecules, ammonia, methane, and water into the growing planet, locking away the fingerprints of the early solar system. In a way, Jupiter is a time capsule, a planet-sized archive of what the universe looked like 4.5 billion years ago. As its mass grew, something remarkable happened, a runaway effect. The more material Jupiter gained, the stronger its gravity became, and the more gas it could attract. Growth fed on itself until the process spiraled out of control, pulling in vast amounts of hydrogen and helium. This tipping point is what turned Jupiter from a supersized Earth into a gas giant dot. Past that threshold, adding more mass didn't make it much bigger, it simply made it denser, compressing its gases under enormous pressure. That's why Jupiter is often called the solar system's heavyweight champion. Even though its radius is not dramatically larger than Saturn's, it is a planet not of bulk alone, but of gravity's deep persistence. There's a popular myth that Jupiter is a failed star. It's easy to see why people say that. After all, it's made mostly of the same gases as the Sun. But the truth is more nuanced. For a planet to ignite fusion to truly become a star, it needs to be roughly 80 times more massive than Jupiter. Only then would the pressure and temperature at its core be high enough to start fusing hydrogen into helium, releasing the steady light of a sun. Jupiter falls far short of that mark. It doesn't burn, it glows faintly from residual heat left over from its formation. In the quiet cold of space, that warmth is a soft echo of the moment it was born, when compression and collapse filled it with energy. So rather than a failed star, Jupiter is better thought of as the closest thing nature allows to a star without fire. Its presence reshaped everything around it. The newborn giant stirred the disk, scattering debris and sending shockwaves through the early solar system. Some of those disturbances helped clear the inner regions of excess material, allowing smaller rocky worlds like Earth and Mars to form safely within. Others flung comets and icy bodies outward, seeding the distant regions that would become the Kuiper Belt and Oort cloud in that sense. Jupiter didn't just form, it acted as a sculptor, shaping the structure of the solar system we know today. Even now, Jupiter continues to whisper stories of its origin through its gravity, chemistry, and motion. When spacecraft like Juno orbit Jupiter, they measure subtle variations in its gravitational field, ripples that tell scientists about its inner layers and the relics of that long-ago formation. Beneath its churning clouds lies a core that may not be solid at all, but a diffuse blend of rock, metal, and hydrogen blurred together under crushing pressure. It is as though Jupiter remembers how it formed, but only in dreams. Imagine it then, billions of tons of dust and ice drawn inward by invisible hands, spiraling into a deepening gravity well. Heat builds, pressure mounts. At last, a world is born, not in a blaze of fusion, but in the slow, relentless embrace of gravity. In the heart of a cosmic storm of creation, Jupiter took shape, a giant knot of light, but of weight. And from that moment on, the solar system would never be the same. Dust and ice became order, drawn into the orbit of a swelling king. The young sun's winds blew across its face, but could not strip away its crown. Jupiter's birth was not just the making of a planet. It was the start of a balance, a harmony between creation and control. In the darkness of the ancient nebula, as the last tendrils of gas drifted away, one world stood vast and new. Its gravity hummed through the silence, its clouds still forming from the breath of a collapsing sky. The king of planets had arrived, and the universe, for a moment, held its breath. Jupiter is not just another planet in orbit around the Sun, it's the solar system's quiet choreographer, its gravitational rhythm keeping everything else roughly in line. If the Sun is the conductor of the cosmic orchestra, Jupiter is the booming drum in the back, setting the tempo. Its mass, more than twice that of all the other planets combined, bends the paths of comets, shapes the asteroid belt, and even protects the inner planets from wandering debris most of the time. Its gravity reaches far beyond its own orbit, subtly influencing the shape and safety of our entire celestial neighborhood. When Jupiter first formed, its gravitational pull was immense enough to rearrange the landscape of the early solar system. Vast swarms of icy rocks and planetesimals were flung outward, sent drifting to the edges where they became the raw material of distant regions like the Kuiper Belt. Others were drawn inward and swallowed by the growing planet or collided with the inner worlds, delivering both destruction and water. Even now, billions of years later, Jupiter's presence still echoes in the motion of countless smaller bodies. Nothing in the solar system moves entirely free of its invisible tug. One of Jupiter's most famous roles is that of the so-called cosmic shield. It's often said that without Jupiter, Earth might be bombarded by far more comets and asteroids than it is today. There's truth in that idea, but it's a bit more complicated than a simple tale of a guardian planet. Jupiter's gravity is powerful but impartial. It doesn't care where objects end up, only that they move. Sometimes it deflects dangerous comets away from the inner planets, tossing them harmlessly into distant orbits. Other times, it can steer them inward, putting them on a direct path toward Earth. It's a cosmic paradox. The same planet that has likely saved our world many times over may also have caused some of its greatest catastrophes. Jupiter is both shield and slingshot, protector and potential troublemaker. It's like a benevolent bouncer who occasionally hurls guests back toward the dance floor instead of out the door. Still, on balance, its presence has reduced the overall number of devastating impacts over the solar system's history. Without its gravitational vigilance, the quiet stability that allowed life to flourish on Earth might never have been possible. Nowhere is Jupiter's shaping power more elegantly displayed than in the asteroid belt between Mars and itself. You might picture the asteroid belt as a dense, chaotic swarm of rocks endlessly colliding, but in truth, it's more like a vast desert sprinkled with scattered boulders. Jupiter's gravity is the reason for that sparseness. The planet's influence reaches across hundreds of millions of kilometers, creating regions of stability and instability that dictate where asteroids can and cannot survive. Within the belt, there are certain places where an asteroid's orbital period forms a simple ratio with Jupiter's. Say it orbits the Sun exactly 3 times for every 1 orbit of Jupiter, or 5 times for every 2. These are known as orbital resonances. And while the math may sound harmless, the result is anything but. Each time an asteroid in one of these resonances swings around the Sun, it feels a small tug from Jupiter in the same direction. Over millions of years, those tiny nudges add up, amplifying the asteroid's orbit until it's pushed completely out of the region. The result is a series of empty zones within the asteroid belt known as the Kirkwood gaps. If you could graph the distribution of asteroids by distance from the Sun, you'd see deep troughs where these resonances clear the space like grooves in a record. Jupiter's steady rhythm writes its signature into the solar system, itself an unseen hand-carving order into the chaos of drifting stone. But Jupiter doesn't just scatter. It also gathers, on either side of its orbit, 60 degrees ahead and 60 degrees behind, lie two enormous groups of asteroids known as the Trojan swarms. These are not random clumps, but stable pockets locked in step with Jupiter's motion by gravity's delicate balance at these points, called Lagrange points. The gravitational pull of Jupiter and the Sun combine in such a way that small objects can remain parked indefinitely, moving along with the planet as it travels around the Sun. The result is a cosmic convoy to vast flocks of asteroids following their king-like banners fluttering in procession. The leading group is named after Greek heroes, the trailing one after Trojans. Over time, astronomers have mixed the names so freely that both camps now host an amusing jumble of mythological characters. Some of these asteroids are large enough to be worlds in their own right, complete with moons of their own, while others are little more than drifting rubble. Together, they form a kind of celestial archive, preserving the conditions of the early solar system in orbits that have remained undisturbed for billions of years. These Trojan asteroids are clues to Jupiter's past migrations. Early in the solar system's history, Jupiter didn't necessarily stay where it is today. Theories like the Grand Tack model suggest that the planet may have moved inward toward the Sun before reversing course and migrating back out. During that wandering, it would have captured material from different regions, sweeping up icy bodies and rocky fragments alike. The Trojans may be relics of that migration, ancient travelers carried along by Jupiter's gravitational tides. In studying them, scientists hope to read the diary of the solar system's turbulent youth. Beyond the asteroid belt and the Trojans, Jupiter's reach continues into the outer darkness, shaping the paths of comets and dwarf planets alike. Long-period comets that visit the inner solar system often owe their journeys to Jupiter's distant influence. Their orbits nudged into elongated ellipses that bring them inward to flash briefly across our skies before being flung back into the cold. Even Neptune and Uranus may owe part of their current arrangement to the early gravitational games Jupiter played. It is quite literally the reason the solar system looks the way it does. Jupiter's balancing act, sometimes protective, sometimes perilous, has shaped the very conditions that allowed Earth to remain habitable. Without it, the asteroid belt might have formed into another planet, perhaps destabilizing the inner orbits. With it, the solar system remains dynamic yet orderly, a blend of chaos and structure that endures through billions of years. Jupiter doesn't simply orbit the Sun, it orchestrates the dance of countless smaller worlds. If you could somehow step outside the solar system and watch it unfold from afar, you would see Jupiter's influence everywhere, its gravity pulling comets into curved arcs, sculpting belts of debris, and holding the Trojan swarms like ornaments on an invisible thread. Every small motion, every shifting orbit, is part of the slow cosmic choreography written by this immense world. And yet, for all its might, Jupiter remains a subtle artist. It doesn't announce itself with fire or fusion, but with balance and quiet power. Its gravitational reach is vast, but its touch is measured, sculpting, adjusting, guiding. It is both guardian and gardener, ensuring that the solar system's garden of worlds remains diverse and enduring. Far from being just a massive ball of gas, Jupiter is a cosmic architect, shaping the solar system's rhythm with every orbit. The asteroids that cluster and the comets that swing past owe their paths to its steady hand. The king does not rule through force alone, but through harmony, the gravity of presence, and as it circles the sun, vast and unhurried, the planet's gravity continues to write invisible lines through space, lines that guide, protect, and sometimes surprise. From the smallest pebble in the asteroid belt to the largest world beyond Neptune, all of them move in some way to Jupiter's silent command. Now follow that pull a little closer, past the orbits and the Trojan flocks, toward the planet itself, where those unseen forces become visible, painted across a surface of clouds and color, seen through a telescope. Jupiter looks like a painting in motion, ribbons of cream, caramel, ochre, and rust swirling across a vast canvas of clouds. No other planet wears such complex colors. From a distance, it appears almost calm, like the soft marbling of coffee and cream. But those serene bands are anything but still. Each hue tells a story of chemistry, temperature, and motion written in layers of cloud hundreds of kilometers deep. To understand those colors, we first need to imagine Jupiter's atmosphere not as a single blanket, but as a towering layer cake of gases and ice. At the very top, high above the bulk of the atmosphere, sunlight filters through a haze of ammonia crystals. This layer forms delicate white clouds that drift across the highest regions, reflecting sunlight and giving Jupiter its bright creamy tone. Beneath that, about 80 to 100 kilometers down, conditions grow warmer and more exotic. Here, ammonia gas reacts with hydrogen sulfide to form ammonium hydrosulfide, a compound that condenses into reddish or brownish clouds. Deeper still, farther than any visible light can easily reach, lie the water clouds, enormous, dense structures of frozen droplets and vapor that behave more like thunderstorms than wisps of mist. These three main necks, ammonia, ice, Ammonium, hydrosulfide, and water form the scaffolding of Jupiter's atmosphere. Together, they paint the planet's face. But the real artistry comes from the molecules that give those clouds their tints. Scientists call them chromophores, tiny compounds that absorb certain colors of light while reflecting others. Their exact identities remain partly mysterious. Some may be complex sulfur or phosphorus-bearing molecules. Others could be the chemical products of sunlight breaking down ammonia or other gases in the upper atmosphere. What we do know is that these pigments are created and destroyed by both chemistry and weather. As gases rise from the deeper, hotter layers below and meet ultraviolet sunlight from above, they react to form new compounds, tinting the upper clouds in soft yellows, golds, and brick reds. The process is slow but constant, Jupiter's own version of aging varnish on a masterpiece. The bands we see, the alternating light zones and dark belts, are not painted stripes at all, but vast circulating rivers of air that flow in opposite directions. The pale zones are regions of rising motion where material from below pushes upward, cooling as it ascends and forming bright ammonia clouds high in the atmosphere. The darker belts are sinking regions where air descends, warms, and clears away the upper clouds, revealing deeper, darker layers, rich in ammonium hydrosulfide and other colored compounds. It's as though the planet is breathing, light rising, dark falling, an endless inhale and exhale of gas and chemistry. These belts and zones are not random. They are the outward signs of Jupiter's immense internal heat and its rapid rotation, which together drive fierce jet streams that circle the planet. The interaction of these winds and temperatures determines how deep each band reaches, what chemicals it exposes, and therefore what color it takes on. Where gases rise, they cool and condense into pale clouds. Where they sink, they dry out and darken, seen from afar. This pattern turns Jupiter into a colossal thermal fingerprint, each band a unique combination of temperature, altitude, and chemical composition. Sunlight also plays its part. Even though Jupiter receives only about 4% as much sunlight as Earth, that light still shapes the atmosphere. Ultraviolet radiation breaks apart molecules like ammonia and methane, creating a cascade of chemical reactions that produce the chromophores responsible for the planet's tan and red hues dotting the uppermost layers. High-energy particles from Jupiter's intense magnetic field join the dance, striking atoms and triggering new reactions. Over time, this slow bombardment alters the colors we see, shifting them subtly from year to year, sometimes brightening, sometimes fading, as if the planet is changing moods. If we could stand within Jupiter's clouds, an impossible wish, since the pressure and temperature would crush and dissolve any visitor long before reaching the deeper levels. The scene would be extraordinary. At the top, the light would be dim and diffuse, filtered through layers of haze. Wisps of ammonia snow would drift like powdered sugar in the thin air. Deeper down, the sky would turn ochre, then burnished copper as the ammonium hydrosulfide clouds came into view. Lightning might flash in the distance, illuminating the outlines of vast convective towers rising tens of kilometers high. Each layer would have its own climate, its own color palette, a world within a world. Even from afar, telescopes can glimpse this dynamic beauty. High-altitude clouds cast shadows on lower layers, creating subtle textures. Long plumes of white appear where updrafts disturb the usual flow, and dark streaks mark places where descending air clears the haze. Instruments aboard spacecraft like Juno can see beyond visible light, peering into the infrared to measure temperature and composition, confirming that these color differences are more than skin deep. They reveal structure, real weather patterns rising and falling in slow, endless cycles. For all their grandeur, these colors are delicate, constantly changing with the planet's shifting chemistry and sunlight. The Great Red Spot, for instance, owes its distinctive hue to similar reactions between sunlight and the gases churned up from below. Yet even its color varies, from deep brick to salmon pink, suggesting that the mix of molecules in Jupiter's atmosphere changes over time. In the grand scheme, the planet is not static, but evolving, a living artwork, continually repainted by physics. Each belt and zone also has its own temperature and depth. The bright equatorial zone, for instance, is relatively cool, while the darker belts are warmer and thinner. In some places, bright plumes of ammonia-rich air rise high, spilling into neighboring regions and forming delicate, lace-like edges to the human eye. These contrasts create the illusion of three-dimensional texture, the sense that Jupiter's face is carved in motion. In truth, it's a projection of energy and chemistry, a map of invisible convection currents, made visible through color. And then there are the hazes, thin veils of particles that float above the main clouds like a misty film. They scatter sunlight, softening the boundaries between belts and zones, giving Jupiter its familiar, blurred beauty. These hazes form when sunlight breaks apart molecules in the upper atmosphere, allowing their fragments to recombine into complex, sticky clusters that drift downward like cosmic pollen over time. They build into sheets that tint the light and help maintain the planet's overall palette. The result is a world that never looks quite the same twice. Amateur astronomers often notice subtle changes from year to year, a belt that fades, a zone that brightens, new spots or plumes appearing where calm once reigned. Jupiter's clouds are dynamic, reshaping themselves on timescales of weeks or months. Beneath their tranquil appearance lies a restless system where heat, sunlight, and chemistry weave together in ever-changing patterns. It's humbling to realize that the planet's beauty isn't painted on, it's born from constant motion and transformation. The colors of Jupiter are the visible signature of invisible forces, the soft glow of physics at work in a realm too vast and deep for any human eye to truly comprehend. Look long enough at those swirling bands, and they begin to feel almost alive. Cream-colored zones stretching like strands of silk, cinnamon belts rolling and folding over one another, faint mists draping the horizon in a hazy veil. A world of cloud and color, forever stirring, forever remade, and yet, for all its chaos, Jupiter's face remains balanced and rhythmic, each stripe holding its place in the great atmospheric dance from above. It's as if the planet has found harmony in turbulence. The colors are not just decoration. They are the language of its weather, the poetry of chemistry written in wind. Now, as we leave the stillness of observation, we turn to the motion itself, the winds that draw these stripes and the forces that keep them flowing endlessly around the king of planets. From a distance, Jupiter's stripes look almost painted on, as if some cosmic artist dragged a brush across the planet's surface and left behind perfect, endless ribbons of cream and amber. But those bands aren't painted. They are winds, flowing with a precision and ferocity unmatched anywhere else in the solar system. The entire planet is wrapped in a symphony of jet streams, each one moving in opposite directions to its neighbors. circling the globe at hundreds of kilometers per hour. If you could somehow float above the clouds and watch the atmosphere move, you'd see the whole planet playing an intricate, silent song of motion. Each band a note, each wind a melody, in a rhythm older than time itself. Jupiter's rotation is the key to its striped perfection. The planet spins once every 10 hours. Even though it's more than 100 times wider than Earth, that means points near its equator move at incredible speeds, over 40,000 kilometers per hour. Such rapid rotation twists and stretches the atmosphere, breaking large currents into narrow jets that wrap around the planet from east to west. Each jet becomes the boundary between light zones and dark belts, separating regions of rising and sinking air. The result is a world that looks as though it has been carefully layered by nature's own centrifugal hand. These alternating bands of wind, some eastward, some westward, form what scientists call jet streams. Earth has a few of them, but Jupiter has more than a dozen, all far stronger and deeper. The reason lies partly in the planet's size and partly in the way rotation interacts with convection on Jupiter. Hot gas from the interior rises while cooler gas sinks. But because the planet is spinning so fast, those vertical movements are constantly deflected sideways by a force known as the Coriolis effect. It's the same phenomenon that helps twist hurricanes on Earth, but on Jupiter, it shapes the entire global weather system. Rising air veers one way, sinking air another, until the whole atmosphere organizes itself into alternating lanes of motion, a planetary racetrack in permanent flow. The light-colored zones are where air rises, cools, and condenses into bright ammonia clouds. These are the gentler, calmer regions. The darker belts, on the other hand, are where air sinks, dries, and warms, creating clear patches that reveal deeper, darker layers. Between them, fierce shear zones form, thin but powerful boundaries where neighboring jet streams rub against each other, generating turbulence, waves, and sometimes vast storms. It's along these shearing edges that many of Jupiter's ovals and vortices are born, like eddies forming where two ocean currents meet. Scientists describe these flows using terms borrowed from fluid dynamics, barotropic and baroclinic. In a barotropic flow, the winds move uniformly with depth, like a solid sheet sliding over itself. In a baroclinic flow, temperature and density vary with height, causing layers to slip and twist relative to one another on Earth. Most of our weather is baroclinic. Fronts and storms form where warm and cold air masses collide. But on Jupiter, much of the atmosphere behaves more like a barotropic fluid, with its powerful winds maintaining their speed and direction deep below the visible clouds. It's as if the planet's weather isn't just a surface phenomenon, but a three-dimensional current, an ocean of air that stretches down thousands of kilometers. For a long time, scientists didn't know how deep these jet streams actually went. Were the stripes just a thin pattern painted on the upper atmosphere? Or did they extend far below, rooted in the planet's mysterious interior? The answer came from the Juno spacecraft, which began orbiting Jupiter in 2016. By measuring subtle variations in the planet's gravity field as it flew past, Juno could sense how mass moved beneath the clouds. The results were astonishing. Jupiter's jet streams extend roughly 3,000 kilometers below the surface, far deeper than anyone expected. That's about 300 times the depth of Earth's oceans. These are not just winds. They're colossal systems penetrating into layers where the pressure is so great that hydrogen begins to act more like a liquid metal than a gas. This deep circulation hints at how Jupiter's interior transfers heat. The planet radiates more energy than it receives from the Sun, powered by slow contraction and leftover heat from its formation. That internal warmth bubbles upward, setting the entire atmosphere in motion. As the heat rises, the planet's rotation twists it into bands, which then interact and stabilize into the striped pattern we see today. It's a dance between energy and spin, gravity pulling inward, heat pushing outward, and rotation shaping the flow into ordered chaos. Each band moves at astonishing speed. Near the equator, eastward winds can reach over 500 kilometers per hour. At higher latitudes, westward jets take over, reversing direction but maintaining roughly the same strength. These alternating streams remain stable for centuries, locked in place by the planet's rotation. The boundaries between them are not fixed walls, but shifting regions where turbulence thrives. Here, smaller storms can merge, stretch, or tear apart, feeding energy into the system like drummers keeping rhythm in a never-ending song from afar. The effect is mesmerizing. The pale zones look like sheets of silk flowing gently in one direction, while the darker belts move the other way, their edges curling and twisting like smoke caught between opposing breezes. Tiny white ovals, storms the size of Earth, drift along these borderlines, spinning gently in the turbulent air. Each one is born from the friction between bands, living for weeks or even years before fading back into the surrounding flow. In the deeper layers, unseen by any camera, these same patterns continue, possibly merging into vast slow-moving currents that encircle the entire planet. It's a level of organization that seems almost musical. Imagine Jupiter as a cosmic symphony, each jet stream a note in a vast chord, each storm a brief solo, and the belts and zones the repeating rhythm that ties it all together. The planet is not chaotic, it's orchestrated. Its stripes are the visible notes of an invisible score written by physics. And though Jupiter's atmosphere may look timeless, it is always in motion. New storms form, old ones vanish, and the balance between belts and zones shifts ever so slightly. The planet's rapid spin keeps everything synchronized, but nothing is truly still. Even now, scientists continue to study how these jets stay stable for so long, why the same stripes have persisted for centuries while smaller details change from year to year. Some models suggest that the deep winds tap into the planet's internal heat, creating a feedback loop that sustains them indefinitely. Others think magnetic fields deep inside the planet help anchor the flow, acting as invisible rails beneath the storm. Whatever the mechanism, the result is hypnotic, a world whose surface is pure motion, structured yet unpredictable, violent yet graceful. Jupiter's stripes are more than weather. They are the planet's heartbeat, pulsing endlessly beneath the faint sunlight of the outer solar system. Look closely, and you can almost hear it. The low, rolling rhythm of hydrogen and heat, the harmony of gas and gravity. The belts and zones move in counterpoint. The jet streams hum in harmony, and somewhere within that ceaseless flow, a single note swells louder than the rest. It is the voice of a storm that has raged for centuries, vast and defiant, turning endlessly in Jupiter's southern hemisphere. For centuries, the Great Red Spot has turned slowly in Jupiter's southern hemisphere. A storm so enormous it could once have swallowed 3 Earths whole. It's the most famous weather system in the solar system, a vast, churning oval that has outlived entire human civilizations. Telescopes in the 1700s first recorded it, but by then it was already ancient, spinning endlessly in the deep ochre atmosphere of the king of planets, at its heart. The Great Red Spot is an anticyclone, a high-pressure system rotating counterclockwise in the southern hemisphere, opposite to hurricanes on Earth. Instead of drawing air inward, it pushes outward and upward, creating a towering dome of swirling clouds. The storm sits between two of Jupiter's strongest jet streams, one moving eastward above it, the other westward below. These opposing winds stretch the storm into its familiar oval shape, like a spinning drop of paint caught between two conveyor belts. Despite the chaos around it, the Great Red Spot endures, feeding on the very turbulence that surrounds it. This endurance is one of its great mysteries. Most storms on Earth last days, maybe weeks, before losing energy. But the Great Red Spot has raged for at least 350 years, and possibly far longer. The secret lies in Jupiter's lack of solid ground. On Earth, hurricanes weaken when they hit land, cut off from their source of warm, moist air. Jupiter has no such surface to interfere. The storm can spin freely, drawing energy from the planet's internal heat and from the endless shear between the surrounding jet streams, like an eddy in an infinite river. It is sustained by motion itself. Its rotation is fierce. Winds circled the edge of the storm at speeds up to 430 kilometers per hour, though the center remains surprisingly calm, a wide eye of high, cold cloud tops floating miles above the surrounding atmosphere. Beneath those clouds lies a layered column that likely extends hundreds of kilometers deep, perhaps rooted in regions where hydrogen behaves more like liquid than gas. The upper layers, visible to telescopes, are only the crown of a much deeper phenomenon, one that may reach into the very weather engine of the planet. Yet even this ancient tempest is changing. Over the last century, observers have watched it slowly shrink. Its once sprawling diameter is now only about half what it was in the 1800s. From a colossal 3 Earths across to just a little more than one. The storm is gradually tightening its grip, becoming smaller and rounder. The cause isn't fully understood. It could be losing energy to nearby jet streams, or simply evolving into a more compact, efficient vortex. Whatever the reason, the change is gentle, measured in decades rather than days. The Great Red Spot isn't dying, it's adapting, reshaping itself in the slow rhythm of planetary time. Its color, too, shifts with the years. Some generations have seen it as a deep blood-red oval, others as a pale salmon or faded peach. Scientists think this color comes from chemicals in the upper atmosphere, reacting with sunlight, perhaps sulfur or phosphorus compounds formed when ultraviolet light breaks down ammonia and other gases. Those reactions create reddish pigments that coat the high-altitude clouds. As the chemistry of Jupiter's atmosphere changes, or as the storm lifts or lowers its top layers, the hue changes to it, as though the storm keeps repainting itself, sometimes bold and fiery, sometimes muted and weary. Through spacecraft observations and telescopic monitoring, scientists have learned that the Great Red Spot is not a flat disk, but a towering structure. The cloud tops rise more than 8 kilometers higher than the surrounding regions. Inside, air spirals upward, cools, and spreads outward, creating a bright outer rim that catches sunlight and contrasts sharply with the darker belts around it. The storm's outer edges are chaotic, constantly shedding and reabsorbing smaller vortices. These smaller storms feed into it like tributaries joining a river, replenishing its spin. It's a perfect example of vorticity recycling, where turbulence itself keeps the system alive. Energy doesn't dissipate. It is transferred, reabsorbed, and reborn within the swirling architecture of the storm. In the grand scale of Jupiter's weather, the Great Red Spot isn't alone. It's simply the most famous member of a vast family of vortices that populate the planet. Smaller red spots, white ovals, and brown barges form and vanish across the belts, some merging to grow stronger, others torn apart by shear. But the Great Red Spot reigns as the eldest, the survivor. It's the solar system's most patient weather complaint, muttering for centuries without ever running out of breath. If you could drift above it, the view would be breathtaking. Below, a spinning oval the size of a world, its edges streaked with white filaments of cloud torn from nearby jet streams. Inside the oval, reddish hues swirl and fade into subtle gradients. Deep rust at the edges, soft peach near the center. Sunlight glints off the upper clouds, casting delicate shadows across the layers beneath. To the human eye, it might look calm, almost still. But beneath that serenity are winds moving faster than any earthly storm could sustain. The dynamics of the Great Red Spot can even be heard, in a sense, when scientists translate atmospheric data into sound. The variations in pressure and speed resemble deep, rolling tones, a kind of planetary hum. It's not literal music, but it captures the feeling of rhythm and endurance. The storm is less like a violent outburst and more like a slow, eternal drumbeat in Jupiter's endless symphony of motion. Despite its immensity, the Great Red Spot is fragile compared to the scale of the planet. Jupiter could swallow it a dozen times over and still have room to spare. Yet in its persistence lies something profound. It reminds us that even in a world of violent forces, stability can emerge, not through stillness, but through balance. The storm survives by interacting with its chaotic surroundings, drawing strength from what would destroy lesser systems. In that sense, it's a living symbol of resilience, an eye of order in a sea of turbulence. As we watch it change year by year, we're seeing not the end of a storm, but a process that mirrors the life of all dynamic systems. Things grow, stabilize, decay, and reform. Perhaps one day, centuries from now, the Great Red Spot will finally fade, leaving behind only a faint trace of its rotation in the planet's deeper winds. But until then, it continues to turn unhurried, ancient and vast, like a thought that never quite ends. From the moment telescopes first glimpsed it, to the close-up portraits captured by passing spacecraft, the Great Red Spot has been our window into the persistence of chaos. It's both a storm and a story, a reminder that longevity doesn't always come from calm, but from the ability to keep moving with the currents of change. And Jupiter has many such stories to tell, for where one storm leads, others follow, swirling, colliding, and weaving their patterns into the endless dance of clouds that covers the face of the King of Planets. Weather on Jupiter is not a passing mood. It's a constant performance. Across its vast cloud-wrapped surface, storms are born, grow, collide, and vanish in a grand cycle of motion and renewal. Every cloud on Jupiter is part of an atmosphere alive with electricity and convection, powered by deep internal heat rather than sunlight. Lightning flashes, wind shears twist, and waves ripple through the planet's endless belts and zones. If Earth's weather feels energetic, Jupiter's is an orchestra tuned to a far greater scale. One of the most striking discoveries about Jupiter's weather came from its lightning. Spacecraft like Voyager, Galileo, and Juno have captured brilliant branching flashes of light illuminating the tops of clouds thousands of kilometers wide. These bolts can be hundreds of times more powerful than any thunderstorm on Earth. crackling deep within the water clouds far below the visible ammonia haze. Their light can pierce through multiple layers of atmosphere, glowing faintly from within, like lanterns under a sea of vapor. Each strike is the result of convection, hot air rising, cool air sinking, water droplets colliding, and static charges building until the atmosphere discharges in blinding electric fury. Unlike Earth, Jupiter's lightning is concentrated near the poles and deep inside the cloud layers, where water exists as both liquid and ice. These regions serve as the dynamo of the planet's weather, fueling vast convective towers that rise through the atmosphere. Imagine an updraft so powerful that it carries water vapor upward for dozens of kilometers before cooling, condensing, and forming towering thunderheads capped by ammonia ice. When those droplets freeze, they release heat, driving the convection even harder, a feedback loop of heat and turbulence that keeps Jupiter's storms alive, far above these deep lightning factories. The cloud tops display an entire ecosystem of storms. Some are temporary bright white spots that drift through the belt's compact, oval-shaped systems known as white ovals. Others are darker, brownish features called barges, often found within the planet's belts. White ovals form in regions of high pressure, similar to the Great Red Spot, but they are smaller and shorter-lived. Over time, these ovals can merge, grow stronger, or fade away, part of a continuous cycle of formation and decay. Barges, on the other hand, are lower pressure systems that appear as holes in the cloud decks, giving glimpses into the deeper, darker atmosphere below. They are the quiet inverses of the brighter ovals, complementing Jupiter's weather with subtle contrasts of shadow and light. Sometimes these storms interact in dramatic ways. Two ovals might approach each other, spinning faster as they draw near, and eventually merge into a single, larger vortex. When that happens, the surviving storm often grows stronger, feeding off the combined energy of both parents. The result is an atmosphere where storms behave almost like living organisms, competing, combining, and evolving. These mergers and absorptions are not rare. Jupiter's belts are full of such interactions, creating an ever-shifting mosaic of ovals, streaks, and filaments, despite the immense violence taking place within its clouds. Jupiter's atmosphere has an underlying structure, a rhythm that keeps chaos in check. The pale zones are areas of relative calm, where air rises gently and forms stable, bright ammonia clouds. These are the serene bands, wide and luminous, where little turbulence breaks the surface. In contrast, the darker belts are wild, storm-tossed regions of descending air and turbulent motion. Here powerful winds shear and twist the atmosphere, spawning vortices and waves that propagate across thousands of kilometers dot together. The belts and zones form a planetary pulse, a balance between stillness and storm, between calm breathing and deep convective energy. In some regions, towering plumes erupt like slow-motion fountains. These columns of rising air can reach tens of kilometers high, topped by brilliant white domes that shine even in the dim light so far from the sun. Scientists have compared them to the shape of mushroom clouds, not in violence, but in form, where heated material rises, spreads, and cools in graceful, billowing layers. These immense upwellings transport water, ammonia, and other chemicals from deep within the atmosphere to the upper levels, helping to mix and refresh Jupiter's weather. They're vital to the planet's storm ecology, the dynamic balance that allows the system to sustain itself over time. Jupiter's Storms also create beautiful wave patterns, long, rippling features that can stretch across the planet. These atmospheric waves behave like ripples in a vast fluid ocean, spreading energy from one region to another. Some form at the boundaries between belts and zones, where jet streams move in opposite directions. Others are triggered by convection deep below, rising upward until they manifest as faint, curving bands in some cases. These waves may even influence the timing of major storm outbreaks, creating long-term rhythms that repeat over decades. The colors of Jupiter's storms reflect their altitude and chemistry. Bright white ovals form where ammonia ice clouds reach high altitudes and reflect sunlight, while darker brown or red regions mark areas where the clouds are thinner or mixed with deeper materials. As storms evolve, their colors shift, recording changes in temperature and composition. Observations over decades reveal that Jupiter's entire appearance, its stripes, spots, and plumes, changes subtly over time, as if the planet is breathing in slow motion. The contrast between the calm zones and turbulent belts creates an atmosphere of balance through difference. The zones are vast, slow, and luminous, drifting almost peacefully. The belts, in contrast, are restless, full of hidden lightning, swirling eddies, and rapid convection. Together, they maintain equilibrium across the planet. Energy flows upward in the zones and downward in the belts, completing the grand circuit that keeps the atmosphere alive. It's a delicate dance of energy, a planetary heartbeat that never stops. What makes Jupiter's weather even more extraordinary is that it's powered mostly from within. Unlike Earth, where sunlight drives the winds, Jupiter radiates more heat than it receives from the sun. This internal warmth, left over from its formation and from slow gravitational contraction, stirs the deep layers of hydrogen and helium, driving convection from the inside out. Every storm, every bolt of lightning, every swirling oval is a manifestation of that buried heat escaping into space from orbit. Spacecraft have captured lightning flashing through the clouds, illuminating the night side of the planet with momentary brilliance. These flashes appear as tiny sparks on a vast canvas, but each one represents immense energy, an instant of raw power inside a world where storms are the norm, not the exception. The more scientists observe, the clearer it becomes that Jupiter's atmosphere behaves like a living system, endlessly recycling its energy and material through storms that both destroy and renew. There is a rhythm to it all. Storms appear, fade, and reappear in slightly new forms, their life cycles overlapping like the verses of an endless song. Jupiter's weather is never finished. It is always in motion, always revising its own patterns. This ceaseless transformation has continued for billions of years and will continue for billions more, an atmosphere that remembers its past only through the structures it leaves behind. Beneath the swirling colors and endless storms, deeper still, the air grows denser, hotter, and stranger. Pressure mounts, hydrogen thickens, and the boundaries between gas and liquid begin to blur. The storms above are only the surface ripples of a much deeper ocean of motion, one that leads into realms where matter itself begins to change. Now it is time to sink beneath the clouds, toward that unfamiliar world of metallic winds and hidden heat. As we leave the king of planets behind, the thought lingers. What does Jupiter teach us? Not only about the solar system, but about creation itself. Every system needs balance. Every structure in the cosmos, from the smallest atom to the largest galaxy, depends on opposing forces finding harmony. Expansion and contraction, heat and cold, gravity pulling inward, pressure pushing outward. Jupiter embodies that balance on a monumental scale. It is massive enough to dominate, yet stable enough to endure, violent in appearance, yet calm in rhythm. Within its storms and magnetism lies the same principle that sustains stars, planets, and even life: dynamic equilibrium. Jupiter shows us that order can emerge from motion and beauty from turbulence. Its endless storms are not chaos, but the steady release of energy in perfect balance with the forces that confine it. In that way, it is a living model of the universe itself, vast, restless, but governed by quiet rules. Every planet in our solar system owes something to Jupiter. When it first formed, its immense gravity sculpted the space around it, clearing debris, steering comets, and defining where smaller worlds could safely grow. Without Jupiter's guiding hand, Earth's orbit might have been disrupted, its oceans lost, or its surface scarred beyond recovery. Jupiter's presence gave the inner solar system time to settle, to cool, and eventually to nurture life. In that sense, every breath we take is linked to its distant, invisible pull. Even today, Jupiter's gravity acts as a guardian. It captures wandering comets, deflects asteroids, and protects the delicate orbits of its sibling planets. Sometimes it even absorbs, impacts itself, taking the blows that might otherwise reach us. In 1994, astronomers witnessed one such moment: the impact of comet Shoemaker-Levy 9, the comet, torn into pieces by Jupiter's gravity, collided with the planet in a series of dramatic explosions, each one releasing energy greater than the world's largest nuclear arsenal combined for days. Earth-based telescopes watched dark scars bloom across Jupiter's face, temporary bruises on a giant. But within weeks, the clouds closed over, the atmosphere healed, and the planet went on as before. It was a reminder of Jupiter's resilience and its role as a cosmic shield. Those fragments that could have crossed Earth's path instead met their end against the vastness of Jupiter's atmosphere. In that moment, we saw not only power, but grace. A planet that absorbs catastrophe so that smaller worlds might endure. And yet, Jupiter is not just protector, it is also teacher. It shows us the mechanisms of nature at their grandest scale: fluid dynamics, magnetism, chemistry, and gravity, all woven together into a living experiment, billions of years old. Studying it helps us understand not just gas giants elsewhere in the universe, but the very physics that builds and sustains stars. It even holds clues to how planetary systems beyond our own might form. Astronomers have now found hundreds of exoplanets that resemble Jupiter, some orbiting close to their stars, others drifting far away. These so-called hot Jupiters and super-Jupiters have expanded our understanding of what's possible in planetary creation. By comparing them to our own Jupiter, scientists can trace how planets migrate, interact, and stabilize over time. Jupiter, in that sense, is the archetype, the original template for worlds of its kind across the cosmos. But there's also something more personal in its story, something quietly human. When Galileo first aimed his telescope at the planet in 1610 and saw its 4 bright moons, he wasn't just making an observation. He was taking the first step toward a new way of seeing the universe. Those little dots of light, circling Jupiter, shattered centuries of belief. They showed that Earth was not the fixed center of everything, that there were other centers, other systems, other possibilities. From that single discovery, our vision of the cosmos began to expand, and in that expansion lies the same wonder that still guides us today. Whenever we look at Jupiter through a telescope, on a spacecraft image, or even as a bright star in the night sky, we're looking at a world that connects us to the origins of knowledge. The planet is not just an object of study. It's a symbol of discovery itself. It stands for curiosity, for the simple, timeless act of looking up and asking what else is out there. Perhaps that's why Jupiter inspires such peace when we gaze at it. Despite its size, it doesn't threaten. Despite its storms, it doesn't rage. It simply is steady, magnificent, and eternal. In a universe full of uncertainty, Jupiter represents constancy. It reminds us that even in the midst of motion and change, there can be calm. If you could drift near the planet, beyond the reach of its radiation and storms, you would see a view beyond imagining. Jupiter's clouds rolling below in slow, stately motion, its moons glinting in the soft, reflected sunlight. Beyond them, the distant glimmer of the sun, a tiny point in the vastness, and all around, silence, the perfect, infinite quiet of space, broken only by the hum of electromagnetic waves and the faint whisper of the solar wind. In that silence, Jupiter turns unhurried, immense, enduring. Everything we know about it today comes from centuries of patience, from small glass lenses, from passing spacecraft, from data carried across the void. Yet even with all our technology, the essence of the planet remains the same mystery that first called to Galileo, a bright wanderer in the night, both familiar and unfathomable. In that way, Jupiter is not just the king of planets. It is the heart of wonder, a reminder that exploration never truly ends, because as long as we keep looking outward, we are also looking inward, back toward the question that began it all. Where did we come from, and how does it all fit together? Jupiter doesn't answer that question, but it shows us how to ask it patiently, humbly, and with awe. The planet's storms continue. Its auroras burn. Its moons glide silently through their orbits. And somewhere on a small blue world hundreds of millions of kilometers away, we watch, still learning, still listening, still dreaming. So, as you close your eyes tonight, picture Jupiter, its pale stripes, its ancient red storm, its quiet family of moons. Imagine their slow orbits, the soft glow of auroras flickering over the poles, the deep hum of metallic hydrogen moving far below the clouds. Let the vastness of it soothe you, the scale, the calm, the certainty. You are part of this universe too, born from the same dust, shaped by the same gravity, warmed by the same light. The king of planets turns on, keeping its eternal vigil in the dark, whispering across time that beauty, balance, and motion never truly end. Sleep now beneath that same cosmic rhythm, the quiet breath of Jupiter and the endless harmony of the stars.